Um, Anybody have any questions about homework or anything like that before I start with new stuff? We're moving on to a new topic today. Internal loads. Yep, that's right. Okay. Um, so the new topic is internal loads. We're only going to do internal loads in beams. And a beam is a long, slender body um, with other loads besides axial forces. All you have, so if you have a long, slender body like this and the only loads on it are parallel to the axis, then if the loads are always going to be just axial like that, then you don't call it a beam. I mean, people tend to just, an I-beam is an I-beam no matter how you load it. But when I talk about beams as a general topic, I'm talking about long, slender bodies that in addition to loads like this, also, they can have forces like this, and, they can have couples and stuff like that. Okay. So these bodies have to support loads that are more than just axial. And the motivation for internal loads, the best I can think of, is this. So here's you. I'm so strong, I'm going to break this pencil. Don't think you're all cool. Anyone can break a pencil. Okay, so here's the pencil. Okay, that was stupid. Okay. Yeah, that's true. It's a pretty long pencil. Okay, so if you try to break this pencil by flexing it, okay, so here's the motivation. Here's what we're doing. The motivation isn't trying to break a pencil. This is just helping you understand what internal load is about. Okay, so what does a free body diagram of that stick look like? So there's the stick. Your fingers are applying a downward force and your thumb's applying an upward force. And there's symmetry, so it looks the same on the other side. And so, maybe we could call this F, 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 something like that. Okay, so if all we have to go on are the external loads on this pencil, it's drawn wrong. Okay. Okay, if all you have to go on are those external loads, and you were asked where this pencil was going to break, if you didn't have any experience, bending sticks or whatever like that, you would look at this and you'd say there's 4 places where this could break. One of those 4 places. But from experience that, so from the external loads, you'd get the sense that the fracture would occur at one of those 4 locations of those forces F. But that doesn't agree with experience. That's not what happens. In practice, if you do this, the fracture is going to happen somewhere in between your thumbs. Right. So the fracture would occur between the thumbs somewhere. So if it's not the external loads that determine where something's going to break, we need some other way to measure where a fracture is going to happen. We need another way to predict this fracture. And it turns out that fracture happens, that fracture occurs at spots where the material itself applies large loads to the adjacent material. And these loads that the material applies to itself are called internal loads. And so that's what this is about. Really, this is kind of like the first topic where we're starting to get at the question, where is this thing going to break? And, or I guess, is this thing going to break? And if it is, where is that fracture going to start? Okay, which is going to be a big topic of mechanics, one whole branch of mechanics from now on. So you start with this, and then you go to stress and strain analysis and deform, and then you keep going in that direction after. Okay, so let's think about how to get at this. So let's say we have this beam. And there's a 500 Newton force there at the two ends. And an upward force of 1,000. If you plug this stuff into Newton's laws, you'd see that it's in equilibrium. And let's say that we want to know at this point here, let's see, what are the loads applied to the left piece by the right piece at that chosen line? Okay, well, let's draw a free body diagram of the left piece. So this is what we're isolating. And, you know, and I always say don't do this in free body diagrams, but I'm going to draw an outline of the stuff that we're ignoring just to help you keep your bearings of what we're looking at. Okay, so our free body is that black piece. There's a downward force on the piece that we're analyzing of 500. That red line happens before we get to the 1,000 Newton force going up. So, that 1,000 Newton force would be like here, but we're not looking at that. And then there'd be another 500 Newton force like here, and we're not looking at that. Okay. So now go around the boundary and look for places that the surroundings apply loads to our chosen body. There's one location that I've missed. That's right. At the contact between what we're, right at that line that arrow is pointing to above, the piece that we're isolating makes a fixed joint with the piece that we're ignoring. Okay. And so what are the loads that a fixed joint applies? Yep. So we have an unknown force vector, R, and we also have a couple, M. We want to calculate R and M. Those are the internal loads at that line. So Newton's second law says 0, negative 500 plus Rx, Ry is equal to zeros. And the moment equation, I'll use this as the about point. So there's no moment produced by the 500 Newton force because it acts at the about point. There's the couple M, and I didn't give a distance here. Let's give this distance. So let's say that this is 0.25 meters. This is 0.25. This is 0.5. Okay, so the x component of that force R doesn't produce a moment because its line of action goes right through the about point. The y component does, though. You see that the y component of that force would make this beam rotate around the about point. What's the moment arm of that y component of R? So if we have this upward force at the end here, the horizontal distance is 0.25. Okay, so the moment arm is 0.25. The force vector is Ry. And would that, if that Ry is positive, would that make it rotate clockwise or counterclockwise? Counterclockwise, so this is positive. That's because this is a counterclockwise rotation. And so that's equal to 0. And so now this system of three equations tells us that the vector R is equal to 0, positive 500. And the moment M is equal to negative 125 Newton meters. Yep.
If we drew a free body diagram for the right half, would the moment be the same?
Okay, so that totally anticipates the next thing that we have to talk about with this. Uh, so, so let me ask other questions, and we'll get back to that. That's kind of the next big thing we have to address. Anybody have any other questions about that idea? So what we have is somehow, we don't know how yet. We don't know how this compares to other parts or how much the material can withstand or anything like that. But somehow these loads represent how likely that beam is to break at that line that we chose, at that point along the beam that we chose. Okay, and so if we're trying to figure out how likely this thing is to break, we'd like to know what these internal loads are everywhere along the beam, compare the different parts, and then we'd like to compare that to what that material can withstand. Yep. Yeah, that's a good question. We're sort of gonna, so there at that 1,000 Newton force, there's a discontinuity in the graph. That seems like it would be a big deal. But it turns out it's not really going to be. We're going to sort of gloss over that fact. But so we'll do that too. What we want to do eventually is, instead of looking at this point by point like we did here, we just chose one point to do this calculation. We want to come up with expressions for these internal loads as a function of x that represents the whole beam. So that's our goal. Okay, but we're starting out with just a single point. So this is the basic idea. The basic idea is at every point on the beam, and just as an aside, we're not really talking about points. We're really talking about vertical lines or cross sections. Yeah, exactly. We want to calculate the loads applied to the material by the fixed joint with the adjacent material. Okay. And I would recommend that you try to remember that, because the next thing we're going to do is going to sort of obscure that simple idea a little bit. But one complication comes up. And that is that we really want to know, we want a set of internal loads that that represent so we want a set of values that represent the internal loads at that cross section, no matter how we calculate it. And the problem is, if we had chosen to isolate the right side, and calculate the loads applied by the left side, all of our values would have been equal and opposite. And so we don't really want that. We want to be able to calculate this any way we choose and have the results be consistent. And so because of that, we're going to choose a new sign convention that's independent of the vector directions, the axis directions. And so at the end of the beam, we're going to define those loads applied by the fixed joint as a tension, T, a shear force, V, and a moment, M. Okay? And the way that eliminates the inconsistency between going from the left and the right is if we were going the other direction, if we isolated the right part, we could call a positive value of internal tension a force this way, positive value of shear force up, and a bending moment this way, and then we get the same values either way. But I just wanted to bring this up to point out that still all we're doing is calculating a force vector and a couple, because that's what's applied by a fixed joint. We're just using a new weird sign convention because there's this inconsistency that comes up that we wanted to deal with. So you're going to have to get used to this new sign convention, but still all we're doing is representing a force vector and a couple. Okay. Any questions about that? Oh, this little line? I don't know, because I just like it to look nice. It's just it's not a hat, it's a little flourish. It's just, he's self-conscious about his appearance. Okay, so let's do that same problem that we just did, but now we'll use that new sign convention. Okay, so again, we have the 500 Newton force down at each end, and then the 1,000 Newton force up. And we want to calculate the internal loads at that line. So I'll draw a free body diagram of the left. We have the 500 Newton force down. We haven't gotten to the 1,000 Newton force. And then we have the tension, the shear force, and the bending moment. And those new directions, well, the only one that changes directions is what we called RY before. Now we have the default direction is down. So whereas before an upward force would have been called positive RY, now an upward force would be called a negative V. So Newton's second law, 0, negative 500, plus 0, negative V, is equal to zeros. I forgot the T. Is equal to zeros. And so we get that T is equal to 0. V is equal to negative 500. And the moment equation, we're always going to use the about point at the left end, the left end of the whole beam. So there's no moment produced by the 500. There's a positive bending moment, M. And then there's a moment arm of 0.25 for the force V. And if that value V is positive, that force would be down, and that would cause a clockwise rotation, so this is negative. And this is equal to 0. So M is equal to positive 125. Yep, dang it. You're right. Yes. For the V or for the M? So we already have a value for V, negative 500. So I take this negative 500, plug it in for V. It says M then is equal to 0.25 times V. The M or the V?
I mean the V.
The V would make it rotate. If this was the hinge and you pushed it this way, it would rotate clockwise. So that's why we have a negative here. And then if you move that to the other side, you have M is equal to 0.25 V. Then plug in negative 500 for V. And you get M is equal to negative 125. Any other questions about that one? Okay, so now that's kind of all there is conceptually to calculating the internal loads at a single X value, at a single point along the beam. But now we want to start to try to figure out how to calculate the internal loads for every point along the beam. And obviously we can't sit there and do, we can't just one by one do this at every point because there's infinitely many points. So we need some way to calculate these internal loads as functions of X. But let's start out by just, I'm going to calculate those internal loads for a few different values of X, and I'm going to see what's similar and what's different as we look at these different values. So the next step is to represent the internal loads as functions of X. So let's think about this beam again, the same one. And let's calculate the internal loads, let's say here. And we already did it here, and let's do it here. And let's do it here and here. Okay, so where this distance is 0.1, this distance is 0.1, this is 0.1, and this is 0.1. Okay, and we're going to look at the free body diagrams and see where there are not just numeric changes, but qualitative changes in what the free body diagram looks like. Okay, that's going to tell us something about the way that we're going to have to treat the internal loads as we generally like deal with all these x values. Okay, so for the first one, so let me number these. So let's call this 1, 2, 3, and 4. Okay. So the free body diagram at line 1, what does that look like? We have the downward force of 500. We haven't gotten to the 1,000 yet, so the only other loads are these internal loads, T, V, and M. And now let's look at a free body diagram of point 2. We're still in all of these, the body that we're isolating is going all the way from the left end, but we're just changing where the right end of the thing we're isolating is. So we still have this 500 Newton force going down. We still haven't made it to the 1,000 Newton force, so the only other loads are T, V, and M. Okay, so these two are qualitatively the same. The numbers won't be the same, but the free body diagrams look the same. Okay, so you look at that and you think, well, maybe it's going to look the same for all of them. But we're going to see that these next two, 3 and 4, are going to look different than these first two. So let's draw those free body diagrams. So body 3, we're still now and through all of internal loads, the piece we're isolating goes all the way from the left end of the beam up to the line that we care about. So we still have that 500 Newton force. But this time, we're going from the left end of the beam a little bit past that 1,000 Newton force. So this has to appear in our free body diagram. Okay. So now we have this 1,000 Newton force, and then we have the internal loads, T, V, and M. And so once we started dealing with x values bigger than 0.5, we have a new look to the free body diagram. Okay, these two, maybe we can figure out a way to treat those the same mathematically. This one is going to have to be different. Okay, and the same thing when we isolate body 4, it's going to look like this. The numbers would be different, but we're still going to have the 500, the 1,000, and the internal loads. Okay, so now we have the 500 newtons. We have the 1,000 that's closer towards the middle of what we're isolating. And then we have the internal loads. And these two are qualitatively the same. Yep.
We do it from the right side as long as we just put the signs of M, T, and B.
Yeah, you could. Although I think what you'd rather do is just do it always from the left. It works fine, yeah. But I think it seems to work better for people to just always do it the same way. You're less likely to make mistakes. Yes. That's a really good question. So you always want T to be, we're not going to do problems like that, but that's something that you have to deal with. You always want T to be parallel to the beam. You always want V to be perpendicular to the beam. So you could do those with unit vectors. Or you could use rotation matrices to re-express things in a rotated coordinate system. All right, so the basic story from this is that for any x value from just to the right of the endpoint to just to the left of the 1,000 Newton force, we can treat those all with one free body diagram, and we can treat those mathematically the same. Okay. As soon as you get past this point load, you have to represent your isolated body with a new free body diagram. Okay. So there's something important about those point loads. So the result is that T, V, and M are going to be piecewise functions of x. And the subfunctions, okay, well, before I write that, remember what piecewise functions look like? So we're talking about, like, say, T of x is going to be equal to negative 500 for x on the interval from 0 to 0.3, positive 500 for x on the interval 0.3 to 0.4 or something like that. Okay. And these things in here are called the subfunctions. Yes?
You need to change the point 3n to be a bracket, or you need to place something so that.
Yeah, that's sort of getting at the same question that Ellie was asking earlier. It seems like that would be a big deal. To mathematicians, that would be a big deal. But to us, it's not a big deal because we're infinitely close to any point, and we're really just going to gloss right over that, and it's not going to cause any problems. So we don't know what happens exactly at that point, but we know what happens as we get infinitely close to it from one side, what happens as we get infinitely close from the other side. Okay. Yeah, it seems like that would be a big deal. Turns out it's not something we're ever going to address. We're just going to leave that uncertainty there. So let me reword this. So what x values are candidates for the subfunctions changing? Well, first you have to deal with the endpoints. That almost doesn't even need to be said. And then anywhere where there's any kind of point load, and then the last one is, we're not going to do this yet, but when we start using distributed loads, any places where the distributed load function changes. Okay. Okay, so let's use this one example one more time, and we'll try to come up with functions for internal tension, shear force, and bending moment. So what are the internal loads for all x values? We have 500 down at the other end, and then 1,000 up. Okay, well, let's find all the places that, all the candidates for those subfunctions changing, first of all. We have the two endpoints. And now, besides those two endpoints, are there any other places where there are point loads? In the center, yep. And then we're not using distributed loads, but you'd also look for where the distributed load function changes. You could think of this as like n equals 3. And so we're going to need n minus 1 or 2 free body diagrams. And these free body diagrams are called cuts. Okay, so cut 1 is valid for all x's between 0 and 0.5. And I'm just going to draw one general free body diagram. So there's a 500 Newton force down. No matter what x value we choose in between 0 and 0.5, we haven't made it to the 1,000 Newton force yet. So the only other force we have is T, V, and then the couple M. And how long is this piece? Well, that varies, right? Because this piece can have any length in between basically 0 to basically 0.5. So we're just going to call this x. This distance is x. And we're going to calculate the internal loads as a function of x. Okay? So Newton's second law says 0, negative 500 plus T0 plus 0, negative V is equal to zeros. And so T is equal to 0, V is equal to negative 500. So far, that distance x hasn't come into it. And now we'll go to the moment equation. And like always, for internal loads, our about point is going to be the far left end. The 500 Newton force doesn't produce a moment. M just adds on as M. Then V has a moment arm of x, a magnitude of V, and that downward force would make it rotate clockwise. So minus Vx. T doesn't produce a moment, so those two add up to be 0. So m is equal to Vx. And so the bending moment is equal to negative 500x. Okay, so that's our first set of subfunctions. And these subfunctions are valid for any x inside the interval 0 to 0.5, not including the endpoints. Okay. And now we have to do a cut that represents x values from 0.5 to 1. So cut 2 is for x's in this range from 0.5 to 1. Now you might think that the free body diagram I'm going to draw for this second cut would start like at the value at x equals 0.5 and go some distance past. So remember, in every example we've done so far, where we chose those finite points to analyze the internal loads, we started all the way at the left of the beam, and we're going to keep doing that. Okay. So this range from 0.5 to 1 just represents the possibilities of where the right end is. Okay. On the left end, we're always going to start at the left end of the beam. So this free body diagram has a 500 Newton force down. Somewhere before the end, it has a 1,000 Newton force up. So that's different than the last free body diagram. And then we have the internal loads, T, V, and M. And now let's think about the distances. What's the distance from the left end to this 1,000 Newton force? 0.5, yep. So that doesn't change, right? And no matter what x is, no matter where the endpoint is, it doesn't change where that 1,000 Newton force is. So that distance stays constant. But what does change is the distance from the left end to the right end, and we're still going to call that x. Okay. Now Newton's second law says 0, negative 500 plus 0, 1,000 plus T0 plus 0, negative V is equal to zeros. So T is equal to 0 again. V is equal to positive 500. And then the moment equation with the about point at the left end. The 500 doesn't produce a moment. The 1,000 has a moment arm of 0.5. And is that clockwise or counterclockwise? Counter, so that's positive. Plus m minus Vx, that the plus m and the minus Vx always show up, and that's equal to 0. So m is equal to negative 500 plus Vx, and so m is equal to 500x minus 500. No, because we have the plus 1,000 on there too. For this equation right here.
Yeah.
So we have positive 500 is equal to negative V, so move the V to the other side. So V is positive 500 there. Another question? Okay, so these subfunctions are valid for x values between 0.5 and 1. And so now we're not going to take the time to write them this way usually, but you could now write that t as a function of x is equal to 0 no matter what. V as a function of x is equal to negative 500 for x between 0 and 0.5, and positive 500 for x between 0.5 and 1. And then bending moment as a function of x is equal to negative 500x for x between 0 and 0.5, and 500x minus 500 for x between 0.5 and 1. And, you know, you can, to visualize this, you can plot these functions. So t, if that's 0.5, and that's 1 for the x value, the internal tension is 0 the whole way because we didn't have any horizontal forces. Dang it. The shear force as a function of x is negative 500 on the first half, positive 500 on the second half. And we're just going to connect those, like, just to emphasize how sloppy we're being about the discontinuity there. We're just going to pretend like, and actually, the fact is, there's no such thing as a point force. You know, that's an idealization that we make. Any force is spread out over some small amount of distance, you know. And so if you had this 1,000 Newton force that was spread out over a millimeter or whatever, what you would really get, if you did this calculation, we can do this once we start doing distributed loads, it's something that would look almost exactly like this. It would just have a slight, tiny little slope that would go diagonally from here to there over the length of a millimeter. So this really is about what it looks like. It's just that in our idealization, that's a vertical line. Yep. Distributed loads. So we'll have beams that have distributed loads on them, and if you change the representation, the function that represents the distributed load, then at that point that's a place where the subfunctions are going to change. But we don't have that yet. That's only once we start doing distributed loads. Okay, and then the last one is the bending moment. And that function, it starts out as negative 500x. That's a linear function that goes from 0 to negative 250. And then a linear function that goes from negative 250 to 0. Okay, so we don't have any way to say yet, yes, this thing is going to break, or no, it's not going to break. But we already have enough information to say where we're concerned about it breaking. So if there was one place in this material where you wanted to bulk, say you wanted to thicken that beam or something to make it less likely to break, based on this, what would that be? Yeah, right at the middle, because as you approach the middle from either side, you have the same shear force. Okay? So that doesn't make any distinction between the points. But you can see that the bending moment that's required gets bigger in absolute value as you get closer to the middle. And so somewhere right around the middle is where we're concerned about this. Okay? That's the kind of thing that you want to think about in an engineering analysis of a machine or whatever. Okay.
That's the second graph stand.
The second one is the shear force. So the first one is the tension as you go across the beam. The second one is the shear force as you go across the beam, and then the bending moment. Okay, so let's do one now. Where we start out. So normally you're not given the external loads at the start. So let's say we have one where there's a pin joint at one end. And a roller at the middle. And then at this end, there's a downward force of 1,000 newtons and a horizontal force of 500 newtons. So if this is 1 meter and this is 1 meter, what are the internal loads? Well, before we get into the internal loads and worry about cuts and stuff, we have to find the external loads. First, we need the external loads. So I'll draw a free body diagram of the whole thing. At the pin joint, we have an unknown force vector. I'll call that RA. At the roller, we have an upward force. I'll call that RB. And then here we have the 1,000 down and the 500 to the right. And I'll put the about point here for the rotational equation. Oh, by the way, so I'm doing all of the moments for these. When I do the moment equation, I'm just calculating the moment arm, the force, figuring out whether it's clockwise or counterclockwise to get the sign. If you want, you can do all of those using the rho and the force and the moment, writing out the table. By the end of this, I guarantee that you'll find that it's a lot quicker and more convenient with these beam problems to just figure out the moment arm and the force and the direction. But for now, if you want to write out that whole table, do it. You know, it takes a couple extra seconds and it works perfectly. Okay, so Newton's second law says RAX, RAY plus 0 RB plus, I'm going to lump these two forces together, so 500 negative 1,000 is equal to zeros. And then the moment equation, there's no moment produced by the force at the about point. What's the moment arm for RB? Yep, 1 times RB. And then is that clockwise or counterclockwise? Counter, so that's positive, yep. And then the horizontal force doesn't produce a moment. The vertical one does. What's the moment arm for the 1,000? 2, yep. The force is 1,000. And is that clockwise or counterclockwise? Clockwise, so that's negative. And those add up to 0. So RB is equal to 2,000. And so RA is negative 500 for the x component and negative 1,000 for the y component. Okay, so now we have, here's what we know. Now we know we have a 500 Newton force over here to the left and a 1,000 Newton force down. And then in the middle, a 2,000 Newton force up. And then at the right end, 500 Newton force to the right and a 1,000 Newton force down. Okay, so now let's figure out the candidates for the subfunctions changing. The endpoints. And then besides the endpoints, are there any other points with point loads? Yep, here. So n is equal to 3 again. That means we're going to need 2 cuts. Okay, so cut 1 is valid for x's in what range? 0 to 1, yep. The free body diagram has the 500 and the 1,000 at the left end. Haven't made it to the 2,000 yet, so now we just have T, V, and M. Newton's second law says negative 500, negative 1,000, plus T0, plus 0 negative V is equal to zeros. So T is equal to 500, and V is equal to negative 1,000. So all we're doing now is we're making a cut where the right end of our piece falls before we get to the 2000. So the 2000 Newton force is over here somewhere. And that's not part of the body that we're isolating.
So we need to assume those ones on the left side.
So yeah, the first cut we're making starts at the left end, and the right end is some value. We don't know what it is, but it's less than, it's not enough to make it to the 2000. That'll happen in our second cut. And then the moment equation, we're always going to use about points at the left end. Those two forces at the left end don't produce a moment. And then we just have m minus vx is equal to 0. M is equal to vx. And so m is equal to negative 1000 x. And that subfunction is valid on the interval x between 0 and 1. And now we'll do the second cut. This is valid for x's between 1 and 2. But our free body diagram still goes all the way from the left end. It's just the right end that's between 0 and 2. Okay. So we have the 500 and the 1000 at the left end. Now the right end is past the 2000 Newton force, so that's in there. And then we have the internal loads, T, V, and M. What's the distance between the left end and the 2000 Newton force? 1 meter, yep. And what's the distance between the left end and the right end? X, yep. So Newton's second law says negative 500, negative 1000, plus 0, 2000, plus T0, plus 0, negative V is equal to zeros. And so T is equal to 500. And V is equal to 1000. And then the moment equation, our about point is at the left, so these two don't produce a moment. What's the moment arm of the 2000 Newton force? 1. And is that clockwise or counterclockwise? Counter, so that's positive. And then we have plus m minus vx is equal to 0. So m is equal to negative 2000 plus vx. So m is equal to 1000x minus 2000. And these subfunctions are valid on the interval x from 1 to 2. So let's plot these out. So the internal tension. On that first half of the beam, we had 500. On the second half, we had 500. So that's constant the whole way with a value of 500 newtons. By the way, if you get a positive value of tension, it means that the beam is in tension, it's being pulled apart. If you get a negative value, it means it's in compression. Then the shear force. On the first half, it's negative 1,000. On the second half, it's positive 1,000. And then the bending moment. On the first half, it's a linear function that goes from 0 to negative 1,000. And then the second one, if you plug that into a graphing function or whatever, it turns out that's all a linear function that starts here and goes back to 0. And so the story on this one is about the same as the story on the one before. We did have tension in this one. We didn't before. But we're most concerned about this breaking near where that 2,000 Newton force is applied. Any questions about that? Okay, that's it.